EXTC department of PVTP COE, and I am here to give the orientation for the subject radio frequency modeling and antennas, having subject code ETC 504. This is the outline of my presentation. The subject scheme, the reference books, subject objectives and outcomes, mode of delivery, syllabus plan, applications and experiments. The subject scheme. The teaching scheme, it consists of 4 lectures per week and practicals per every batch of 2 hours. The examination scheme consists of a semester pattern of 80 marks for the theory paper, and there is midterm exam and end-term exam, the average of which will be taken as 20 marks and will be combined together. The term work consists of 25 marks and there is a practical plus oral exam for 25 marks. So overall we can see that there are 150 marks. These are the reference books. The main reference book for the RF part is the first one, that is the Ludwig book. The second and the third book, that is Constantine Balanis for antenna theory, analysis and design, that is for antennas, and John T. Cross, that is J.T. Cross. These 2 books are considered to be the Bible of antenna, whereas the first one, it mainly covers the RF part. The subject objectives. Basically, the subject is a combination of RF, that is radio frequency circuit design, and antennas. Earlier there were 2 different subjects, one was RF-CD and another one was antennas. Both the subjects have been fused together to form RF and antenna. The first 2 modules are of RF, whereas the 3rd, 4th, 5th and 6th module comprises of antennas. However, the first 2 modules itself are so large that they are as good as 3 to 4 modules. That much syllabus coverage has to be done. Now, what are the subject objectives? If we see, the students will be given an exposure to filters, basics of filters. What is basically a low pass filter, a high pass filter, band pass filter, notch filter, comb filter. So these basics will be taught. Afterwards, they will be taught about the magnitude response and the phase response. That is, magnitude is nothing but the real part squared plus the imaginary part squared, and phase is tan inverse of Im by R. The same concepts which they will study here will go on in the next semester in DSP for magnitude and phase. So, apart from that, the basics, what I said, that low pass, high pass, band pass, we'll have different higher types of filters that they will be taught to design. Then, for the antenna part, basically the parameters of antenna should be known, such as gain, radiation resistance and several other parameters. The various characteristics of different types of antenna. As we proceed with our presentation, we see the different types of antenna that are there in the syllabus. Outcomes. After studying this subject, the students should be able to design different kinds of RF filters. When they go in the industry, they should be able to design the filters based on their needs. So the basics are taught here in this subject and they should be able to understand. Analyze the radiation mechanism of antennas. As I said that there are different antennae in the syllabus, they should be knowing how each antenna radiates. Then demonstrate the knowledge of antennas in communication systems. How in wireless communication they can use the antennae. And ability to discriminate the antenna on the basis of their electrical performance. As we know, an antenna can have a physical structure and we can say that it is a particular antenna based on its structure, loop antenna or some other antenna. However, there will be electrical parameters also, electrical properties of the antennas, based on which it will be discriminated. Mode of delivery is blackboard and chalk duster plus the presentations. As such, in the oral syllabus, we require 52 lectures given by the university. However, the required number of lectures will be around 56 or 58 lectures, which I will cover it. The syllabus plan. This is the week number 1, 2, 3, 4, then 5, 6, 7, 8, 9, 10, 11, 12 and 13. So the first module, behavior of active and passive components in RF range, this consists of 4 lectures. That means the first week is assigned to it. However, the module is too large, so more than 4 lectures would be required because the concepts of AWG and several other things are to be considered over there. The second module, which has been assigned 12 lectures, so it will require second week, that is 4 lectures, third week, that is 4 lectures, fourth week, that is again 4 lectures. However, these 12 lectures are not enough to complete this much syllabus. So for module number 2, at least it should be around 18 lectures that I would require to cover, or even more than 18. Actually, module 1 and module 2 itself required 25 to 26 lectures last time. Then, fundamentals of antenna. Now, the students who have come from diploma, they had some exposure to antenna, as they have seen the different shapes of antennas, what is a microstrip antenna, Yagiuda antenna, and several other antenna, loop antenna. However, the students who are coming here after 12th standard, for them these fundamentals of antennas are really new concepts, as well as for the students who are coming from diploma. So we are studying the different parameters of antennas, basically such as the gain, radiation resistance, directivity, beam width, beam solid angle, beam efficiency, and there are many more. Then the Friis transmission equation, which is the equation required for the transmission reception purpose, PR equal to PTGTGR, lambda upon 4 pi r the whole square. This will also be derived over here. Then there are certain other derivations such as the maximum directivity and maximum effective area. Then fundamentals of antenna, it will also cover the radiation mechanism for basic types of antenna. Next module that we have is the wire antenna. Here there are several derivations in this module for different types of wire antennas. Basically, wire antennas means any wire which has been given a particular shape. That will require 10 lectures, so it will be 8, 9 and the 10th week. Antenna arrays, that will be for 1 week. Again over there, 1 week, that is 4 lectures is not sufficient, so more than 4 lectures will be required. And special types of antennas, that will require 12th and the 13th week. Now, behavior of active and passive components in the RF range. We will study about the frequency spectrum, the different frequency bands which are assigned. That will be discussed in this module. Then, hazards of electromagnetic radiation. As we say, the mobile phone emits electromagnetic radiations, so as well as the microwave oven. So students will be taught over here what are the effects of these radiations, and so they should be keeping these equipments away from their body. What are the hazards that are caused due to the heating of the body parts? How biologically the biological substance, that is a human body, can get affected. They will be taught about the specific absorption rate, and that is dependent upon the biological, how much the electric field is accepted by the biological substance, that is the human body. So there are different topics covered over there under hazards of electromagnetic radiation, as to how much every electrical device radiates and how much every human being would be absorbing it. And so based on it, they have given some conclusions that radiation towers should not be placed on buildings wherein there are old people, that is old age homes, because when the age is more, that time the body does not accept that much, does not have that much resistance to withstand that much radiation. Similarly for the school buildings, that is why these norms are made that on school buildings as well as for old age homes, we should not have the mobile towers. Moreover, it has been said that the radiation affects those people who remain in continuous exposure to the radiations. For example, if the mobile tower is mounted on the building, on a residential building, then housewives, those who do not go to work, as well as the old people, they are the ones which will come in exposure to the main beam of the antenna. as we know that the main beam of the antenna contains maximum energy, that is the maximum radiation. So those are the people who will not be going outside the home, they will be permanently in the home. So the radiation effects will be more for them. Then radiations and fundamentals of radio frequency design. So concepts over here that will be considered such as the skin effect, skin depth, and many more. Then high frequency behavior, equivalent circuit, and the frequency response of resistor, capacitor, and inductor. Here we will first see the ideal behavior of a resistor, ideal behavior of a capacitor, and ideal behavior of an inductor. And further we will see how they behave at higher frequencies. Resistor will not just behave like a resistor at very high frequency. Then the characteristics, structure, and applications of coaxial line. So there will be mathematicals also in over here, that they have to calculate the line parameters for the coaxial line, microstrip line, and the coplanar lines. Then skin effect is also over here, and the skin depth. Skin effect, first of all we will talk about DC. When we are talking about DC, the entire cross section of the wire will be utilized. That is, the flow will be through the entire cross section if we cut a wire. Whereas in case of the AC, the current will have a tendency to flow only towards the surface, that is towards the periphery. That is towards the center, it will be hollow. There will be nothing. And this effect is known as the skin effect, and this is a very important concept in RF. Then skin depth. It is the depth of the conductor up to which the conductivity falls to 1 upon E. That is, when you take 1 upon E in the calci, it comes out to be 0.37 some value in decimals, and if we convert it into percentage, that comes out to be 37%. So that is the depth up to which the conductivity is there. Then internal and external inductance. The internal inductance we can denote it by a capital L. L, we know that it is known as the inductance, and L in, so known to be the internal inductance, and Lx known to be the external inductance. The internal inductance is the inductance which is inside the current carrying conductor, whereas external is the outside one, and together it is known as the Lin plus Lx, that is the total inductance. Then resistors and high frequency. There are different types of categories under this. Again, there is chip resistors, that is, it is of a small chip, and there is the code over there, the length and the width. This is a basic structure of a chip resistor, and it will have some length L and W, and that is the width. This is the length, this is the W, and say suppose there is a code over it 0402. So this is the known to be the size code, and the length over here is considered in terms of tens of mils. That is, the length of it will be 10 into 0.4, that is 40 mils. Mils is a unit, and this will be 02 into 10, that will be 20 mils, 20 mils. And 1 mil is equal to 0.001 inch. Now, filter designing. Under filter designing, we have the basic two methods. One is the image parameter method, another one is the insertion loss method. The image parameter method comprises of a lot of topics under it, even the insertion loss method. And the insertion loss method further will have applications in DSP subject again in the next semester. Again, the filter transformations which are being done here in the 5th semester in RF, again they will come in the next semester in DTSP. So these topics are going to come again in some other form. Basically, we will talk about periodic structures. Any structure which we say that will repeat after a particular shape, after a particular same interval, is known as a periodic structure. So they can be any periodic structures. Like we can take an example of a cube in which a particular design would be changing again and again, and after a certain extent it will repeat. So that is coming to be a periodic structure. So we can have periodic structure in our theory as well. So now let us talk about the image parameter method. So image parameter method. Under the image parameter method, we have the constant K-type filters. What the first one what we have written. Under the constant K-type filters, we will have the low pass, constant K low pass filter, constant K high pass filter, constant K band pass filter, constant K band stop filter. Under each one, almost we will have its T section and its pi section circuits, and there will be derivations for almost each one of it, of which even in Ludwig book they are not given completely, whereas I have derived each and every value of the inductor and capacitor in my notes, so everything is available for the students. So this is the first thing. From the student's point of view, these type of questions are such in which they should be knowing all the derivations. That is, in every say suppose there will be the T section, there will be the pi section, there will be the T section circuit over here, there will be the pi section circuit over here. Students should know the derivations of it. They should know every value of L and C, or 2C, 2L, whatever that has come over here. Moreover, if directly sums are asked, they should know the values by heart also. So if sums are asked, they should know the values by heart, where is which inductor, which capacitor. If derivation is asked, they should know the derivation also completely. And it has to be kept very clearly understood in the mind, else students usually create a confusion over here and they end up designing something else. Again, under high pass, there will be the T and the pi. Band pass, again there will be T pi. Everywhere there will be value of inductor, everywhere there will be value of different capacitors. Each value will have to be derived. And then after derivation, the mathematicals will start, that is the sums. So, just talking about the constant K-type filters. So just as an example, constant K-type filters. Over here, the K, or that is a constant, then that is why they are known as the constant K-type filters. The series impedance over here, series, as we can see, that is the series arm over here, series impedance Z1, and shunt impedance Z2, shunt, that is this arm, are related by this relation. Z1, Z2 equal to K squared equal to R0 squared, and R0 is known as the design impedance or the nominal characteristic impedance. The Z1, which we are seeing series impedance, it has been splitted over here, Z1 by 2, Z1 by 2. Over there it is Z1, and the capacitor over there it is divided, that is C by 2, C by 2. So this is the T section, pi section. There is complete derivation for this as to how that these values have come. Moreover, circuit also has to be known to the student. And similarly, this is just an example that I have given. Similarly, it is to be known for all. This is just constant K low pass, T pi. Similarly for others. Now, what we are seeing over here is that the design impedance Z1, that is the total series arm. We have seen over here, we have the series arm. In the series arm, the impedance we have taken is j omega L, whereas for the shunt arm, they have taken it to be 1 upon j omega C. Now, this is for the constant K-type filter. For low pass we are considering, and for T and pi both. Whereas when we are going to go for the high pass filter, this is going to become reverse. Z1 value is going to be the one which is now at Z2, and the Z2 value is going to be the one which is now at Z1. So finally, when we are going to multiply the two, Z1, Z2, it is going to become L by C. So R0 is equal to under root of Z1, Z2 is equal to under root of L by C ohm. And here we conclude that since the product of Z1, Z2 is equal to L by C, which is going to be some constant value, that is why it is known to be a constant T-type filter. Now, Again, there is cross verification over here of how we can understand what model sum we have done is right or not.
Sir, you are designing for some frequency. There is no any frequency equation. But
there is. Here I have only mentioned in short. I have all derivations. That is what I am coming there only. That if certain frequency is given, frequency will be given, and based on it, when we are going to calculate the value of L and C, exactly R0 is going to come. Say suppose 600, R0 value was given to be 600 in the question, and based on all the derived formulas which we will be applying, we will be calculating the value of L and C. Just we have to put the value of L and C. On calculation also, the answer that we will get will again be the same, which is given in the question for R0. So this is the way how we can cross it. That was the same answer, sir. Then similarly over here, T section of constant K high pass filter, T section of constant K high pass filter. There are many more which I will be covering later. Then insertion loss method. After completing the image parameter method, there is one more topic over there in image parameter method. There will be the M derived filters in the image parameter method. This one, M derived filters. Based on constant K, we will be having M derived filters. Why the name M derived? Because these filters are derived from constant K filters. So basic structure of constant K is to be known, and then from that we will be deriving it. Again over here, how is it? Under M derived, we will first have the basic structure of T and pi. As of now, I am not saying low pass or high pass. I am only saying just the T and pi section of M derived filter that we will derive. We will see what is the shunt arm over there, and we will derive what is the value of M in case of the T and the pi. And then we will apply the concepts every time to these filters. That means when we are going to do M derived filters, see, so first as I said, we will be doing the T section and the pi section analysis, and then we will move on to similarly low pass, high pass, band pass and band stop. So every time when we are going to derive M derived low pass filter T section, we are going to look at the circuit of constant K low pass T section, and there every term is going to be replaced, and then we are going to derive the circuit for this one. Again for pi, we are going to do the same thing. Even for M derived H pass, high pass, we will go for high pass of constant K. This will copy, we will compare and then derive. Again for this, again this way. So these filters are completely derived from the constant K filters. That is why the name M derived filters, and M is nothing but a parameter that we derive from it, which is included everything in the notes, the derivations. Then composite filters. Now composite filters are a combination of the constant K filters and the M derived filters. Say suppose we have a particular circuit, and then we are going to connect it this way. Say suppose these cables are connected in layman's language. So it is this way, that at both ends these are same. So we connect two matching sections at both the ends. We know the theory of transmission lines, and we know that both the sides we should have some common, the characteristic impedance, input impedance, both sides, Z in, Z0. So both sides we have the matching sections. And say suppose this is matching section 1, that is matching section 2, and here we will have the constant K type and we have the M derived. So all these are combined together to form what is known as the composite filter. So in order to design a composite filter, the knowledge of constant K filters, the knowledge of M derived filters is to be completely known. And this is a question which is usually asked in the exam for 10 marks. Design a composite low pass filter or design a composite high pass filter. Then after that, the fundamentals of antennas. This module will talk about the various basics of antennas, such as the gain, radiation resistance, directivity, beam width, beam efficiency, beam solid angle, and several other antenna parameters. Basically, we can say that 60% of that module is just based on derivations, the standard derivations. So, first of all, when we talk about an antenna, we say that the antenna is a passive device. We know what are active devices that will generate its own signal. However, the antenna does not generate its own signal. It will take signal from somebody else and it will give. It is only doing the work of being a medium between the electromagnetic waves which are through the transmission line, and they are becoming the free space waves. So the fundamental parameters of antenna over here, we'll study about the gain. So gain, we know how we define it for the output upon input for the active devices. However, we do not design gain, we do not define gain for the antenna in that way, because antenna being a passive device. So there are different definitions of gain for the antenna. So at least I have some 10 to 11 pages or definitions of gain that we can have. Gain with respect to isotropic antenna, gain with respect to directivity, and many more. So those parameters are covered over here. Then radiation resistance. Radiation resistance is a fictitious quantity, we say, and it should be as high as possible. Actually, we say that that if radiation is going out, then means it is some loss. However, in case of antennas, that loss is considered to be a good loss, because why? We want that radiation to come out of the antenna so that it reaches the destination. So radiation resistance. Then directivity. Practical antennas that we use in our life are having directivity. There are concepts over here such as the isotropic antenna, which is a hypothetical concept. We say that the directivity of isotropic antenna is 1, and it radiates equally in all the in the area of a sphere. However, practically it does not happen, because ideal case which we consider is only for the comparison. Then directivity. So coming to the directivity, as we said, that all antenna cannot be isotropic in practical. So directivity means the antenna will be radiating more in one particular direction and less in another direction. The best example of this is a Yagiuda antenna, which was used in the 90s on the rooftops, which was mounted for the television reception purposes. So for that antenna, it radiates, it will receive signal more in one direction, it will be less in some other direction. So then aperture. We know that when we say aperture, we can imagine that there is some sort of opening. So obviously, when we talk about that, that is a physical aperture. However, in terms of the electrical parameters, there will be the physical aperture AP and the effective aperture AE. The AE will talk about the electrical properties of the antenna in terms of the voltage and the current and the impedance. So that is there. Then beam width. We know the beam width of the antenna will be focused in one particular direction, so that it will radiate more in that direction. To understand this, first of all, we will see the concept of lobes and nulls. Basically, when the antenna is radiating, we can say that this is the major lobe of the antenna. That means it is radiating the maximum energy in this particular direction. So the antenna should face in that direction. This is the front lobe of the antenna, and this is known to be the back lobe. There will be some side lobes over here as well. Then there are some terms that we define for the antenna. The radiation intensity that we consider is considered to be maximum over here, that is 1. Radiation intensity means that is the intensity at which the antenna is radiating the signal. This, as we said, this is the major lobe of the antenna, this is the back lobe of the antenna, or the front lobe and the back lobe. So there is a parameter known as the front to back ratio. That is how much radiation is going in this direction to the back direction. Obviously we know that the ratio should be as high as possible, because when the numerator term is going to be high, that means this value is going to be high, and we want backward radiation to be less. The radiations which are in all the different directions are known to be the unwanted radiations or the spurious radiations, which we have to suppress and keep them as small as possible, because they represent the loss of the energy. Then there is a term called as the first side lobes. As we said, these are the side lobes, all these are the side lobes. However, the side lobes which are immediately next to the main lobe are known as the first side lobes, and these side lobes will be smaller in size than the main lobe. However, they will be larger in size than the remaining side lobes. lobes. That is the concept of the side lobes, first side lobes. Then there is a concept called as the stray factor, the ratio of the area of the back lobe to the front lobe is known as, to the total area, is known as the stray factor. Then it is a concept over here of considering the beam width. Obviously we can say that this is the beam and we have the width of the beam. The front, the half power beam width and the first null beam width. The half power beam width and the first null beam width. This is the first null beam width that we call. It is called as a first null beam width because where the nulls are occurring, the nulls means the position where there is no radiation. At that position, at the first position itself, where the nulls are occurring, that is known as the first null beam width. Whereas when the radiation intensity is equal to half over here of the main lobe, where it cuts and goes, that is known to be the half power beam width. Other parameters related to the antenna, the main equation as we said, we have the Friis transmission equation, in which we consider that one antenna is transmitting from one end and another antenna is receiving from the other end. And we derive the equation that is PR equal to transmitted power, PR equal to PT GTGR lambda upon 4 pi r the whole square, in which we consider the transmitted power, the received power, the distance between the two antennas, the lambda, that is the wavelength. Wire antennas. This module, as we say, a wire can be of any shape. We can have a wire and bend it into any shape, it will give radiations or it will receive the radiation. Even a single wire of straight wire left as it is will radiate. However, as we say in theoretical concepts, that the wire should not be infinite in extent. It can be bent, it can be given into any particular shape, that is fine, but it will be finite in extent. So we have a concept of infinite simul dipole and small dipole. The concept of infinite simul dipole is used only for the study purpose. Just like earlier I said that isotropic antenna concept is used only for the theoretical purpose. Then small dipole, large dipole, based on the different lengths of the dipole, we have classified those different the dipoles, and we have the derivations in a syllabus for the radiation resistance of a small dipole, radiation resistance of a lambda by 2 half wavelength dipole, that way. Then finite length dipole, then monopole antenna. See, suppose this is a rod and on which there is one antenna, so it becomes a monopole, that is a single pole. We can see that it would be having omnidirectional pattern, that is it will be radiating in a plane, as we cannot say that it will be having isotropic pattern. Then loop antennas. Any antenna bent and connected at one end electric supply can be known to be the loop antenna.